All right, well, welcome back everybody into the second video in our Chapter 8 series, where we're going to continue looking at the addition of elements across a carbon-carbon double bond. We started this in Chapter 1 where we looked at this in kind of a general sense, but now we'll look at some more specific examples and focus a little bit on the mechanism and how we get to the final products. So what we want to focus on in this video is the reactions called hydrohalogenation, where we add a hydrohalide acid across the carbon-carbon double bond, so things like HBr or HCl in particular. So let's take a look at just kind of a general representation of this particular reaction. Here we have a carbon-carbon double bond, HBr, and adds across that double bond to generate an alkyl halide. Now, last chapter we spent a lot of time looking at the reverse of this particular process, where we would take an alkyl halide of some kind, we choose a particular set of conditions based on the structure of the alkyl halide, and we could facilitate the reverse of this reaction where we would produce a carbon-carbon double bond as the product. What we want to do here is take a little bit look in some more detail at the sort of the mechanism of how this goes. We'll see some similarities between the elimination mechanism and a couple of other sort of features about this particular mechanism. So let's look here at a new substrate. Here, if we imagine a cyclohexene with a couple of methyl groups on it, and if we want to focus on the steps of the mechanism, what we would observe here, for example, if I have HBr, what I would imagine here is that double bond, and we talked about this a little bit in the first video, where we could imagine it acting as a nucleophile, and in this case our electrophile is the proton. On this HBr, of course, an exceptionally strong acid, pKa up around 9 or so for that particular acid. And so what we would imagine here generating as an intermediate would be something that would look like this. Just showing the lone pairs on that bromide atom, bromide ion, remembering that it's there. And of course now we've seen this enough times that we can imagine that bromide acting as a nucleophile to attack that positive carbocation charge, satisfying the carbocation charge, and leading here to the final product. So again, we get a carbocation, or we propose a carbocation intermediate. And so the evidence for this carbocation intermediate, part of the evidence, among other things, is that we get a racemic product. So we get a racemic product, so that's evidence of that planar carbocation intermediate. If that didn't occur, if we didn't get that flat sp2 hybridized planar cation being formed, we might expect some different outcome in the stereochemistry, but in this instance, we get a racemic product, suggesting that planar carbocation is truly the intermediate on this particular pathway. Let's look in some more detail about the regiochemistry of this as well. So if we imagine an unsymmetrical alkene that we're working with here, again, I'll put methyl cyclohexane. So now we've got two different ends to the double bond. We've got one end that's more substituted than the other. And what we observe in this reaction with HBr, and I'll draw it as an equilibrium, and we can talk a little bit later as we kind of put this together about whether it would be an equilibrium or not, but I think it would be relatively straightforward for us to believe that's the case, because we've seen plenty of examples of the reverse reaction of this, where we have an alkyl halide going to produce an elimination product. So HBr adding across there, and what we observe is that the bromide, that the nucleophile in this reaction winds up on the most substituted carbon. Now, I think we're at the stage where this makes an awful lot of sense to us. If we're suggesting that there's a carbocation intermediate, we would predict by far and away that tertiary carbocation would be the predominant cation formed in this particular reaction. By far and away the predominant cation formed in this reaction, and would lead us to the product that's observed there upon reaction with that bromide nucleophile. So you'll see our textbook, and you'll see several other textbooks refer to this as the Markovnikov product. This is the Markovnikov product, but it follows everything that we've come to know about the structure and bonding of these kinds of functional groups, and that nucleophile adds where we would expect, because it would proceed via the most stable carbocation. So it's welcome if you remember the Markovnikov product and think about it that way, but I think it's more useful if we kind of think about it in terms of what the structure and bonding rules tell us about. There is a very brief mention in our textbook, and if you're looking at other organic chemistry textbooks, you see reference to what's called an Anti-Markovnikov product. And so that's the product that looks like this. In the presence of HBr and in some kind of peroxide. What you observe is that the bromide, or the nucleophile, winds up at a position that is not the same as what we would have as goes by a carbocation. So what I'll say, so this is referred to as the Anti-Markovnikov product. The Anti-Markovnikov product, what I'll say about this mechanism here is that it's not a carbocation. It proceeds by a radical mechanism. And you'll see more of those radical mechanisms in Organic 2 for those of you that are sticking around to take that particular course. So I'll leave this mechanism alone here at this point, just to show that there is another outcome. Our textbook refers to it kind of briefly in passing, so I thought I'd mention it here as well. Okay, so what other evidence do we have for these hydrohalo reactions, addition reactions to go via carbocation intermediate? Well, a couple of other observations that we make that support some of that evidence fall into this here. So again, an unsymmetrical product. Here I'll look at this cyclohexane, methyl cyclohexane with a double bond at that particular position. And what we observe if we react this with HCl, although we see the same, of course, with HBr, but I'll just use HCl here to show that it kind of reacts the same way as we observe HBr. What we observe is the major product. Major product is that, by far, the most substituted alkyl halide, or the tertiary alkyl halide. And of course, those of you that have been playing along at home all this time here will recognize that if we add a proton across that double bond in this direction, we generate something that would look like a secondary carbocation, but of course we've got a hydrogen here that can undergo that 1,2 hydride shift that we talked quite a bit about when we discussed the unimolecular mechanisms in the substitution and elimination chapter. So that would rearrange, we'd get a carbocation rearrangement to generate, of course, by far the more stable tertiary carbocation. And then the final step, of course, would be the attack of that carbocation by the nucleophile, in this case is the chloride atom, which would ultimately lead to the tertiary product there. So again, following a mechanism that we've seen before, adding some very strong evidence, I would say, to the intermediacy of a carbocation in these reactions. And just one last piece of evidence to look at this and add some more evidence for those carbocations. Do we see the same kind of thing that we would observe with the methyl shifts? And of course, the answer here is also we observe the same thing. Again, if we start with, I should put the double bond in here. At that position, if we start with a double bond at that particular position, in the presence of HBr, what we observe is a product that looks like this. We've got and again, here we would add a hydrogen across that double bond. We add that hydrogen across the double bond attacks that proton as a nucleophile. I can draw the arrow in here just to show that what step is happening there. We draw something that looks like a secondary carbocation. But of course we recognize, again, just as we did with the unimolecular mechanisms in Chapter 7, we get a 1,2 methyl group shift to generate a carbocation at that position, which then can in turn, of course, be attacked by the nucleophile. And these are steps I think that are hopefully getting a bit more familiar to us now. I'm going to get attacked by a nucleophile to satisfy that positive charge and leading to that observed tertiary alkyl halide product. So the summary of this particular section here is that those addition of HBr or HCl across a double bond proceeds via carbocation, and the evidence for that not only is in a racemic mixture of the product, but also that we do observe carbocation rearrangement, suggesting there is an intermediacy of a carbocation there, and so that's the evidence for that. So there's the mechanism, there's the use of that particular reaction, following the reverse of things that we've seen, I think, quite frequently in the substitution chapter. And so what we'll do in the next video is we'll take a look more carefully at the addition of the elements of water across a carbon-carbon double bond.